Okay, thank you everyone who sort of hung around. We're sorry we were a little bit late. There was a few technical problems, but we're live here now. And for those of you who have joined us, I'm glad that we've got today from Jacob Sherson from Aarhus University in Copenhagen, not Copenhagen, I knew I'd screw that up, in Denmark, who's sort of a kindred spirit when it comes to the meQuanics project and sort of scientific gaming, because he has led quite a large group in developing quantum games of his own. Those of you who are sort of paying attention to what's going on within quantum computing and quantum physics may have seen a Nature paper about a month ago talking about a game called Quantum Moves. This was developed by the team in Denmark, and Jacob is the leader of this team. So thank you for joining us.
Thank you very much for having me.
So unlike our last two guests, our last two was Anne Broadbent from Ottawa and Christoph Swarve from Microsoft, you do come from the physics community, don't you?
Exactly, yeah. I'm an experimental researcher, and then I'm heading a little bit into these quantum games through that direction.
So did you come up through quantum computing, or did you really come up through quantum physics and now you've gotten interested in quantum computing?
Well, I was originally interested mostly in real quantum physics. So from the sort of most basic angle of doing quantum measurements during my PhD, and now then I moved during my postdoc. I moved then to working with cold atoms, ultra cold atoms. And there we ended up having an experiment with which we had individual site addressability. And that means that we have sort of at our disposal, maybe sort of hundreds of atoms, and we can address those individually. And then suddenly that seems sort of not so distant from quantum computing architecture. And then the interest comes from that.
Okay, so I mean, in your group now, you've sort of built, so we're going to talk about two separate things here. The first thing is sort of science at home, which is more of a package program. It's not one project, it's not one game, it's more of a conglomeration of things, right?
Yes, exactly.
And then on the other hand, there's this recent high-profile paper that you guys have gotten on Quantum Moves, which is a specific project,
yes.
Which is very much more of a subset of sort of your broader research efforts. Is this a fair summary of what you guys are doing?
Yes, so we started out by just making these quantum games, and Quantum Moves is the first of those games, and it comes from my inspiration from just having experimental challenges in the lab, which was trying to deal with moving around individual atoms in ultra-focused laser beams. Mm-hmm. And then it seemed that we didn't get as good results as we could get, and that's why we tried to build these games. And then from there on, we tried also to, whenever we meet people, then we have we cannot stop from finding new common projects with people in chemistry and psychology and cognitive science.
Okay, so let's try and break this up, because obviously I see the angry bird sitting behind you at the moment. So your group now in Denmark is very much focused on this sort of citizen science effort, this idea of gamifying certain problems. Is that sort of the overall? You're not that focused on quantum computing or quantum science. It's about gamification. Is this sort of the goal of your group?
Well, I live two different lives in my group, or I have two different subgroups. One is the experiment. We are setting up the experiment in which we have this individual single site addressability. So we're really trying to build that experiment, and we're really trying to take the solutions that we get from Quantum Moves and implement them directly into the lab. So that means that the online activities are really, first of all, built to support the experiments that we are building and trying to do.
So, I mean, I was looking at your website, and what you've got 20 or so people. Are they the experimental people as well as sort of the gaming people, or are they just the gaming people?
No, that's everyone. So the experimental team is sort of 10 people, and then the next 10 people are the people building the games.
Okay, so Quantum Moves is about this Well, maybe why don't you explain it? It's about optical lattices and about trying to move particles in a potential well. Maybe try and give us an overview,
Yes.
in a minute or so, if you can.
Yeah, so the basic idea is that if you take two laser beams and they are counter-propagating, then that creates a standing wave potential of light. And if you do that from three different directions, then you get this sort of lattice-like structure in which you have light in only these nodes. And then the atoms will actually be sort of sucked into those or attracted to these nodes. And then we have sort of a crystal-like structure which is suspended in midair or in vacuum. And that's the sort of basic core of being able to try to manipulate individual atoms. So we can load individual atoms in there, and by using ultra-focused laser beams, we can also sort of pick up individual atoms. But the problem is that when we start to pick up these individual atoms, and if we want to build a quantum computer of moving around those atoms, then they need to be sort of delivered in the target well in the ground state. So that's very similar to sort of trying to have a cup of coffee, moving it very quickly, and you need to move as quickly as possible, but you need to deliver it in the next room in rest.
So I mean, what's a good analogy of this? So the way I see it is you've sort of got like a well. It's literally a well, and you've got a particle that sort of, as quantum moves sort of suggests, you've got this thing that's sort of sloshing around, and if the well is too shallow, it sort of sloshes out of, and you try to manipulate, as you said, it's like a coffee cup where you don't want to spill over the edge.
Yes, exactly.
But it's happening in 3 dimensions, and it's more complicated than this, or?
Well, it's not so much more complicated. Well, it's a laser beam, so that means we reduce it to a one-dimensional problem, but it's really sort of it's a two-dimensional. It could potentially slosh in other directions, but it will primarily slosh in the direction of the motion. Mm-hmm. So if you move the laser beam only in one direction, then this is a fairly good model of the individual atom moving around. So that means that we believe that we can actually take the solutions from the experiment, from the quantum moves, and implement them directly in the experiment. And so when you play the game, then you see in the game, you see sort of a small container, and then you see this sloshing liquid inside. And the height, when you play the game, the height of your, so the mouse, when you move it up and down, then the bowl moves up and down, and that really contains to, or corresponds to turning up and down the laser intensity, which creates a deeper. Means that your motion with the mouse in X and Y coordinates corresponds to motion in the plane of a laser beam and intensity turning up and down.
So, I mean, the Quantum Moves platform, the Quantum Moves game, this is designed to obviously allow general people to kind of solve the problem and give you, data on the best solution. Is this a hard thing for experimentalists to calculate?
Well, it's actually a hard thing, I think, for theoreticians also to calculate.
Okay.
It turns out that there's something called the quantum speed limit, and of course, in all quantum computer architectures, it's essential for us to do fast computations, right? And that's because there's decoherence in any architecture. There's decoherence, and you need to be faster than that, which means the faster we can drive our gate operations to, the more operations we can have before you have the decoherence time. Mm-hmm. So that means that you really have to be as fast as possible. But then there is sort of a fundamental limitation or a theorem in physics that relates to the presence of something called the quantum speed limit, which just tells you that for a given transformation from one state to another state, there's a minimal time required for that. And it turns out that calculations become sort of exponentially harder as you approach this quantum speed limit. So the faster solutions you want to get, the tougher the solution space becomes to searching. And that's something that one of the main results of our Nature paper was that so far people have actually believed that the way to find or calculate this quantum speed limit was simply to take the best state-of-the-art optimization algorithms and optimize for reducing process durations. And the first process duration at which you could not find any solutions that were sort of 100% good, that identified the fundamental quantum speed limit.
So how far, as
just to finish it,
Oh,
just to finish, because our finding or surprise was then that we first did that. We first let our computer sort of run through 100 million simulations, and we established sort of a limit or a duration at which we couldn't find, or beyond which we couldn't find good solutions. But then when with players, and we plotted the player results in the same curve, then we saw that players actually found solutions that were good at shorter durations than what our optimization algorithm found. And sort of there were two conclusions to draw from that. Either the fundamental sort of quantum speed limit was wrong, and they had actually found something which violated quantum physics, or the a priori sort of assumption in the field that you could just use state-of-the-art optimization algorithms to locate this was wrong. And I think that's just because the problem is just more complex than you sort of than was expected.
Hang on, sorry, I'm a little confused. Are you saying that the player, so you've got the fundamental limit, which you call the quantum speed limit, and that's theoretically based, it's a hard limit. Are you saying that players were finding better solutions than this hard limit, or they were just finding better solutions compared to what you could do using, you know, sort of classical simulation algorithms?
Yes. So what I'm saying is, so the quantum speed limit is a very hard fact, or sort of you can calculate the quantum speed limit, but only if you have a constant Hamiltonian. So if you have a constant Hamiltonian, then you can calculate. It's just a time-energy uncertainty relation. Mm-hmm. But as soon as you have a time varying Hamiltonian, then there are no ways to calculate sort of explicitly or analytically the value of the quantum speed limit, although we sort of postulate that it still exists. So what people have done is, in the absence of having analytic results, people have said, okay, so the way we find this speed limit is by just optimizing our systems, and when optimization breaks down, that must be the fundamental limit. But what we're saying now is that it's not necessarily the fundamental limit that you get when the computers fail. It could just be your computers failing to optimize in a sort of very, very high dimensional space.
So how much better were human players achieving? I mean, if you want to try to put it in a percentage value, you know, were they beating it by 300 or 400%, or were they beating it by 10 or 20%?
They were beating it alone, so that the player results alone were beating it by sort of something like 10-20%. So went 10-20% below the limit that we established. But then what we found was that if you now take the player results, feed them into the optimal, actually violated sort of the bound that we found before by a factor of 2. So that corresponds to a sort of dramatic increase in the speed of the gate operations that we can do. And that just is so my interpretation is just that the players, you have an optimization space which is 1,000-dimensional, so it's impossible to search through all of that. And what the players do is actually they have some sort of intuition for the problem. That means that they search in a very small region, but by chance or luck or intuition, they search in a region in which the good solutions are sort of very densely spaced, which means that you can take that quantum intuition now, and then you can feed it into your algorithm as a starting guess rather than our sort of random starting guess, and then we achieve much, much better results. So it's the intuition of the players combined with the fine-tuning abilities of the computer which leaves the best results.
Right. So what is the sort of the mechanics of the gameplay itself? So I mean, you log into Quantum Moves and you get this sort of potential thing. What's the aim of the game? What are you trying to do?
So for instance, so now since last month we have it on the iPhone and on Android devices. And so let's say that you play with your finger, you tap your finger, and you get to control then the bowl. And your aim is then to move it from where it was initially into the target area. And the idea is then to have it as sort of stationary as possible in the end. And then you're rewarded by what we call the fidelity, which is just the overlap between the target state that we want and the final state after your transformation. And then we introduce also a time bonus in order to push people to find as fast solutions as possible.
So when it comes, it's basically this kind of sloshing thing. So you don't want sort of as you said, the sort of the coffee in the potential world to slosh around too much. When you say sort of the target is fidelity, is there sort of a visual indication?
Yes. So first of all, there's the visual indication that you can see whether it's sloshy or not. In addition to that, we have sort of, when you enter the target zone, then we have sort of a circle which fills up proportional to how good your score is. So you can directly see sort of what the aim of the game is, sort of to move it quickly into the target area, and then it's still sloshing a little bit, and then you need to sort of get the sense of the sloshing and then anti-slosh in order to take out that kinetic energy of the system.
Right.
And you can follow it live. Sort of.
Right. So players don't have to wait until the very end to realize what their score is. They sort of know what's happening as they're progressing through their game.
Yes, exactly. And what my philosophy, I think that, so I've tried to sort of philosophize on what it is that the players are doing. And what I think that they're doing is that games in general allow you to sort of change the rules of physics just a little bit. So we tested whether knowledge of quantum mechanics actually helps you in playing the game, and we saw no effect. But what I think is happening is that the games and the rules of the games are based on the time-dependent Schrödinger equation, so quantum physics. And players who know nothing about quantum physics, they are at first sort of puzzled a little bit about the way that the atom sloshes around. It doesn't behave exactly like a liquid. And for instance, it also does this quantum tunneling when you have two wells nearby each other. And at first, people are puzzled by this, but then they sort of accept that and start to incorporate that into their own logic. And then you get these very powerful algorithms that are sort of based on very much on normal sort of sloshing intuition, but just a little bit of adaptation to quantum rules. And I really compare it to, I don't know if you could know this game of Portal.
Yes.
Yeah. So I think it's the same there. So you walk around in this universe, and then it's the regular universe, except that you can actually activate a portal, and then you can go into one place and you go out the other place. And at first you don't really know how that should enable you to do things that are not physically possible. But then you see that these new rules, they allow you to do things that are sort of not normally possible. And I think the same thing happens on an intuitive level to our players in Quantum Moves.
Great. I mean, so obviously, especially before the Nature paper, so you developed this platform and you released it, and you got quite a large number of players, and that certainly allowed you to develop the data that eventually went into the Nature paper. But once the Nature paper was released, from what I saw, you got an explosion of players coming into the site, playing the game, and giving you a whole stack of new data. Now, I don't want to preempt any scientific stuff that you might be presenting soon, but how did that change things?
So it changes things in two ways. One way was just that it was fantastic to see and plot in sort of the same plot as we presented in Nature, but now with more and more and more points. And what we see is, to our sort of big surprise, players just keep moving further and further into this regime of very, very fast solutions. So now we have, with the 130,000 people who has played it in the last month, we have much better results already than we had in the Nature paper. So it just shows that going in and getting more and more data and getting more and more people in and engaged with this keeps getting and generating more and more better data. So that was one thing that was great for us. The second thing is that we are now sort of moving to stage 2 of the project, in which we are trying not only to generate new and good results, but also to understand why we humans are so good at generating these much better results than the computer. So we're starting to incorporate machine learning algorithms into the analysis then of the player results. We can extract then the features that characterize good solutions. And then it's really interesting to look at not the final solutions, but the path towards the final solutions, in the sense that we take all players, we bunch them in the successful players and the not so successful players. We characterize the successful players, what characterized them, and then we look for the sort of practice runs that the good players had. And then we can identify what their strategy of learning was. And the hope is that we can incorporate this now into sort of machine learning or optimization algorithms in general, and get this sort of human intuition or human problem-solving strategies into more complex algorithms. And then we can start to get rid of the games again and solve complex challenges a little bit more efficiently than we could before.
This is a good divergence, because I mean, certainly with meQuanics, we're trying to do the same thing, basically to use human data to try and train AI or train machine learning. One question that I wanted to ask you about your project was the problem that we've tried to face is that we need high retention. We need people who come in to play the game and don't just play it once, don't just play it twice. They come back again and again. They optimize more their solutions. They come in and they try and do better. In your experience with Quantum Moves, do you have a metric for retention? How many people come back, or is it just one-time players? Is one-time players all you need? Or do you need people to come back and refine their solutions and compete against other people?
So there are two issues to that, and I think we generally observe, of course, that the longer we can get them to stay, the better results we will get out of them. But still, even with people playing just a little bit, we actually get something useful from them after their first few trials, when they have sort of built this sort of basic way of attacking the problem. Then we can start to analyze that and get sort of some insights from it. And I think one thing that different platforms is to have a look at the sort of cognitive abilities that each game, your game, our game, all other games, are based on. Because I think that we can probably distinguish these games from games that are sort of puzzle type games, in which you have to acquire some knowledge about it, and then you think about it, and you actively sort of consider a solution. And then I actually would place our games in another category, because when you play the games, each individual game only takes about 1 second or 2 seconds or something like that. So there's really not too much time for you to actively sort of consider what you should do. It's much more sort of an intuition-based game, and that's what I think that maybe that's why we get a better output from players much sooner, because we don't rely on, let's say, cognitive training or conscientious training, but rather sort of intuition training. And I think that would be really interesting to look at across your platform and our platform and see what the differences are.
So literally that sort of first level, when you first log into Quantum Moves and you play that first puzzle that pops up on the game, from that point on, you guys are collecting data that's actually useful data. You don't have to step a player through 5, 10, 20 levels before you get to the stage where useful data is being collected.
Well, of course we've tried to make to place the, let's say, more interesting and more challenging problems a little bit later on in the game. But it doesn't. So that we would like people to sort of get to, for instance, the level 13 is the one that we talked about in the Nature paper, for instance. But we also have sort of a quick link in which you can just go directly from the entry screen and then onto level 13. If you read the paper and you want to try exactly that level, then people can go there, and playing that a couple of times or a few times, we can already see that they are starting to contribute to some of them actually get very good solutions, but some of them also have this solution which becomes a good solution when we put it into the computer. So for us, we have this sort of two-step process in which things that may not seem extremely useful from a player point of view, you get 10% out of 100, that may actually provide the best ever result when we feed it into the computer.
So the way you collect data, is it an aggregate thing, or, as you said, is a certain player's approach to a problem, when you feed it into your subsequent algorithms, that produces the result? It's, you're not amalgamating this data with 20 or 30,000 other people to get this result. It could be one person.
Yeah, exactly. So that could be one person, but what we found from all the different players was we found something really extraordinary. I think when we took all the players who played it, and then we try to sort of take we try to take all the solutions that they have generated and then generate sort of what you could call a distance map. So how distant were all of these solutions from each other? And then to our surprise, we saw sort of patches. And it seemed like across players, there were two distinct ways of trying to play that game. And then, of course, we could take all, we call these clans. And then when you take all solutions that are similar to each other and average those out, then you get curves that we can start to interpret. So each curve by itself has all kinds of wiggles, and it's hard to say what they actually mean. But averaging all those wiggles out, we could really interpret what the underlying strategy really was in each of these solution strategies. So, and to our surprise, that's where we were again surprised, because it was not really the solution strategy that we would have thought of in a sort of classical educated quantum physics sense. So if you take any double well problem and I tell you, okay, you should tunnel from one well to another well, and you get to control one well, then 9 out of 10 or 99 out of 100 physicists will tell you, well, match energy levels exactly, and then you will get transfer. And that's how we would have played the game, but that's not at all how the players played the game. They played the game by sort of using the extra tweezer much more like a shovel, and then sort of scooping the atom up, and then as they sort of dragged the atom with it, then they sort of made minor adjustments to it to allow for the tunneling to happen. Right. So it was much more sort of based on classical intuition than what we would have thought. And I think that was really interesting, that we can start to extract not only good solutions, but also something about solution strategy, something about the nature of the problem.
So in the way you sort of came to this idea and the way you sort of developed it, what was your motivation? Was your motivation to help out experimentalists working with this kind of technology, or was your motivation more about sort of the psychology and the sort of way in which human beings can potentially solve problems better than standard computational algorithmics?
When we started the project, I had no sort of, I had very, very little hopes that would actually be where we ended up, that we would prove that humans were actually better at it. It was sort of more like, I've always had the feeling or the sense that in physics research, we tend to use our intuition a little bit too little. We tend to be too analytical, and we tend to be sort of too conscientious about how we attack problems. And initially I actually didn't want to build games. I wanted to build graphical visualization tools for researchers. So when we work with our atoms in these lattices, then they are governed by something called the Bose-Hubbard model, and I wanted a graphical tool for the Bose-Hubbard model. And then I wanted something to play around with the Schrödinger equation, because then my students could also sort of get, without spending lots of time, they would actually get sort of the intuition about it. And then the inspiration for making it into a game actually came because I was bicycling always 10 kilometers for work every day, and I listened to these hardware software radio shows, and they kept talking about gamification. Not so much in science. It was 5 years ago, so it was not. But they talked about it in industry, and then I thought, oh, if they can try it in industry, let's also try it in science and in physics. And so it started out more sort of as we had these theoretical problems. We had just done the calculations. We'd just seen that it didn't really yield, that the calculations didn't really yield extremely good results, and we thought, okay, let's just try it out.
So, I mean, correct me if I'm wrong, you did a postdoc with Emmanuel Bloch at Munich,
exactly.
who works a lot with these optical lattice stuff. In the context of quantum computing, I mean, where does the physical technology that quantum moves plays with? How is that in terms of development in regards to the sort of broader context of what many people might have seen when it comes to quantum computers or quantum communication systems? So
the atoms in optical lattices have several advantages because they are so pure. There are no phonons in optical lattices because they are just ultra stable because of the light and the interference effects of the light. So So we can cool them. We can, to a very high degree, have very low entropy in our crystals, and that's sort of a good thing about it. The downside, of course, to that type of architecture is that it may be scalable up to, so easily scalable up to, let's say, hundreds of atoms, which is a big step compared to where we are today in other architectures. But then it doesn't naturally sort of lend itself to mass production and to mass sort of scaling up, and so going to millions of qubits in such an architecture is not so so feasible. So it's more sort of on the mesoscopic scale. It easy to sort of jump into the mesoscopic scale rather than the microscopic scale where we are with many architectures at the moment. But really, what the optical lattices are mostly suited for would be the sort of the quantum simulation part of the quantum computation. Could be sort of small scale quantum computations, but very ideally suited then for the sort of massively parallelism in quantum simulations. And so that's what that's where we are saying sort of the quantum moves can be sort of steps towards sort of mesoscopic scale quantum computation, but then also very, very efficient sort of quantum simulation in which you can initialize. It allows you to with very high accuracy initialize also any sort of states sort of that are not produced normally. So we can sort of project any potential landscape onto the atoms, and we can create then sort of any initialization within the not only qubit space, but it can become qubit spaces in the sense that we can put not only sort of one atom on each, but we can have 0, 1, 2, 3 atoms in each well, and create sort of a much richer structure for doing, let's say, general unitary transformations.
But I mean, quantum moves is about, I mean, it's not about how you would manipulate a given atom within its well. It's about how you bring these things together and try to interact them. Is that correct?
Yes, exactly. Yeah.
Okay. So, I mean, quantum moves is not, I mean, quantum moves is obviously the thing that you guys have become well known for now, but it's not the only thing you guys are doing. You seem, certainly from what I've seen on your website, you're doing a hell of a lot more in this sort of gamification space. You're trying to figure out all kinds of different problems that you can solve. So you fill us in a little bit on this kind of stuff?
Yes, so we found out that just by talking to colleagues at other faculties also, that we sort of had a shared language. So when we started to analyze the quantum moves games, then we were led naturally into this landscape sort of visualization. So we picture the control problem as a landscape, and the idea is just to find the top peak in the landscape, and there are many different sort of mountains in that landscape, and that's what makes the optimization problem difficult. And in terms of that methodology or terminology, that is very similar to the problems that they have in corporate innovation, in which they are looking at problems of sort of maximizing profit and who should they hire, physicists or engineers. And that again just defines a landscape. So people are actually in several different fields in the university interested in this way that humans navigate in these landscapes. So we've teamed up with people from corporate innovation, with people from cognitive science, and behavioral economics, and trying to investigate in a more systematic now way how people behave in optimization tasks. So in quantum moves, the landscape was just incredibly complex because we had something like 10 to the thousands different local optima in that landscape. And what we do now is we strip it down to games in which we have just a few peaks, and then we examine both how individuals search around in those landscapes, so that is individual generic search sort of behavior, and then we also have games in which we try to look at collaborative problem solving. So the question is, how should you make teams, and how should you share knowledge among teams in order to make as efficient optimization as possible? So those are yeah, sorry.
So it's not restricted to quantum computing. This is now far more broader of what you guys are trying to look at.
Yes, exactly. So the idea is really to the idea is really to try to take the synergies from what we have learned about problem solving, and then try to see if what we've discovered is that in talking to these other different fields, then in joining up the problems, we can actually bring each of our competences together, and then we actually can advance, I think, both of our fields. So talking to behavioral economists and corporate innovation people actually makes our understanding a little bit deeper of how to solve quantum problems. And on the other way around, we can actually also help teach cognitive scientists and the other researchers, psychologists, understand their problems in a slightly deeper manner.
So have you put any of this stuff online? Because I mean, Quantum Moves is not the only game on your website.
No, so one game that we developed together with the corporate innovation people is called Alien Game, and so it's a game which is online now. You can play it and at scienceathome.org, and then so you can just go there, and then the basic game is that you encounter an alien. This alien has sort of a task for you to, or puzzle for you to solve, and you have 8 tiles, and you have now 25 switches of the tiles in order to find the secret message. So it's like a binary optimization search that you do, and what we study is then how efficiently people understand and comprehend the systematics and the symmetries in the problem and how they attack that. And then so that can be played now. Another game that we have online is called Quantum Minds, which is very much like the games in quantum physics, but we've introduced now a couple of extra slightly non-physical artifacts. One is we have introduced zones of death, which if you hit them, then you die. And that makes the problem much more complex from a computational point of view, because the first seed that you get, let's imagine that you play an ordinary quantum moves, you drag around a particular path, otherwise you hit the barriers. And from a computational point of view, this is extremely complex because the initial value that you get out is 0. You die. Mm-hmm. And with any seed that you give to the computer, you die. And then what the computer does is that it changes slightly the path, but it still dies. But what is interesting in us humans is that we actually have the ability to sort of process the whole multidimensional interface that you see, form hypotheses about why we died, and then also see that although we died again the second time, we maybe died a little bit less. So we get sort of, rather than binary information, we get processed this full information. And that is, we think, sort of on the core to understanding why human optimization is different from computer optimization.
And again, with all of these games, you're actually collecting data. So everyone who plays, you're collecting data coming from what they do.
Yes, exactly. Yeah. So the more we get, the more sort of advanced statistics analysis we can do. The idea with understanding human optimization is also that we would like to, I mean, maybe there's a difference between how old people and young people play the game, and you need to be able to bunch your data then in these 2 different categories, but also male and female maybe, or dog lovers and cat lovers. And every time you add another category, then you reduce the number of data points that you have in each category. That means more data allows you to do more sophisticated analyses.
Are you collecting these demographics, old and young people, cat lovers and dog lovers?
We are collecting a little bit, and we would like to collect more. We are actually working on, together with psychologists, on something which is sort of a gamification of psychology research. So you can say that our basic challenge is to understand what makes a good player in quantum moves. And then you can sort of formulate different hypotheses that sex and age and dog lovers and cat lovers have different sort of dependencies in your explanation model. And what we're building is sort of an easy to use drag and drop in which you can formulate hypotheses, and then you get a score out based on how likely, how good your model is. And that allows you to sort of search through, and we can get the help of all our players in formulating sort of all of these hypotheses and testing them. But second of all, the idea with that game that we're developing now is then also to give people the chance of saying, I think that there's a question that people haven't answered yet, which is, so just for an example, these cat lovers or dog lovers. So some people might say, I think that has some predictive value. So they pose that question, and then everyone who plays the games, they get points for answering the questions. And then whenever sort of your new category is used by someone successfully in generating sort of a new model, then you get points also for that. So that's sort of trying to gamify the whole process of psychology research.
So in terms of what Science and Home is trying to do, are you pushing more in towards the development of quantum technology, or are you pushing more into this kind of gamification and how people can solve problems regardless of field, regardless of problem?
We try to push in those two directions that we have. We try to have several new games. We're working on games based on Rydberg atoms and optimization of sort of gate operations in those. So we try to move deeper into quantum technology, but at the same time then try to have sort of cross-platform games that allows us to learn something maybe a little bit more general. And then the idea is, or the hope is, that from all of these sort of cross-platform analyses, we can actually learn something more generic about sort of human optimization that will enable us then in each of the domains to do normal conventional optimization in a slightly more efficient manner. So that's how we're trying to sort of make it feedback. We've also introduced a new set of games that are also available on the App Store, for instance. They're called Skill Lab, and those are sort of small miniature games which are not science games as themselves, but are supposed to give us information about the players that can then feed into these analyses of who they are. So for instance, you can play Tetris many places online, but you can also play it in our app. And if you play it in our app, then that allows us to correlate your behavior and efficiency of playing Tetris together with quantum moves abilities, and allows us to sort of strip down the core abilities that you need to have in order to be successful in those games. We also have sort of small memory type games and reaction type games, and all of that allows us to build sort of a cognitive profile of our players and then compare that on an aggregate level to how that makes them perform on the real research challenges.
Well, so here's an interesting question. I mean, are you, given certainly the astounding amount of data that you've collected from quantum moves, are you intending to test, experimentally the solutions generated from quantum moves, in the labs? Are you going to design control pulse sequences derived from players and then test them against, what you guys have developed previously?
Yes, that is the intention. We had as sometimes happens in the experiments, we had a minor setback, and we would have liked to test it already now, but we had some problems with our vacuum windows, so we were delayed by about a year. So the hope is that within sort of a little bit more than half a year, we'll actually be able to be able to take the solutions directly from the games and incorporate them into the real sort of movements of the atoms.
Is it a single solution or is it an aggregate solution? Because from the context of our game with meQuanics, one of the very interesting things we thought was having a 10 or 12-year-old kid who happened to provide the one solution, becoming an author on the paper. Is that the way it would work for you guys as well?
We have now identified, so from all the players we have, there's of course one solution which is the best solution, but it allows us also, we have sort of these clans that are sort of continuously deformed solutions of each other, and now that allows us to sort of not only sort of go for the one solution which is the best one, but also have criteria of robustness and start to, so we can actually start to look at the whole clan, and then there are many solutions that are sort of almost equivalent in the output, but then you can start to look at which ones of them are more robust, and that would of course be the more favorable solutions to take. So I think we are, compared to what you said, that we have this one person who was extremely lucky, and we thought maybe in luck, if we have 100,000 people playing it, then one would be very lucky and generate something useful for us. And the big surprise has been so many people generate something useful, and that means that we have sort of a more robust set of results to apply in the lab then.
Sure. Okay, so we're getting to the sort of the second stage of what I like to talk about, and that's to try to get, considering this is supposed to be a podcast for lay people, is to where you see the field is. I mean, the EU just announced $1 billion in investment in quantum computing technology, and you guys may or may not be a part of that. Where do you see the field where it is now, especially in regards to the development of active quantum technology, industrial investment, government investment, and where do you think things are going in the next 5 or 10 years?
Yeah, I think it's really such a fascinating time right now for the quantum computing. I mean, you just have to look around and then see who's starting to invest in the technologies to see that this is really becoming a much more ripe technology. So things are now moving sort of rapidly from being sort of where it was all sort of blue sky research and you had no idea when, and no one would put numbers on when it would actually happen, then to actually now in the quantum manifesto we actually we can start to put numbers to say that, well, it's actually fairly realistic that 5 years from now we actually have something which is vastly much closer to real quantum computers than what we see today. And of course, this accelerated advances are very much spurred in by the commercial interest that we start to have, and will even more so be spurred in or be accelerated by the massive investments that we have by the European Union, in Canada, in the UK. Massive investments have also been sort of very instrumental in allowing for deep focus on sort of on moving from just proof of principle demonstrations to taking it much more seriously. So I think that a couple of years ago, the vast majority of the researchers in the field, they were considering themselves almost entirely sort of proof of principle people, and now the number of groups that actually are starting to take on the task of doing the engineering tasks also is really increasing. And I think that's what really moves the timescales of when we can expect to see quantum computers in a useful sense. That is that people really across a wide range are starting to think that these technical problems also should be tackled in order to have something really realizable.
Well, I do try to put everyone's feet to the fire to give me sort of a prediction in 5 years, so we can, if everyone's still around in the field, we can look back and see who was right. In 5 years' time, where do you think we're going to be? You think 100 qubits, 200 qubits, something that can outperform a classical computer?
I think that we should be 5 years from now. I think that we have seen the first real quantum speedups. And that means that so that is sort of the big threshold that we need to pass. It's not the full sort of, and I think 50 efficient qubits, 70 efficient qubits will really be enough to start to do that, and that should be manageable within the. So let's say I would put say in 5 years, I would be surprised if we didn't have 100 qubits operating at a sort of a decent level. So of course you can always say that you have already 100 qubits in various different architectures, but it's really the number of the number of really operational qubits. Now I'm talking the physical qubits, right? So that depends really. What's really interesting is how how does it pan out in terms of the error correction and the number of physical qubits versus logical qubits that we need, and that's one of the big questions that we are also trying to work on. So from my perspective, I think that what we'll see is also much more emphasis on, at least that's what I hope, much more emphasis on not only placing qubits in decoherence-free subspaces, protected subspaces, but also to use active control to actively stabilize the qubits. And I think that will also be another avenue that can reduce the requirements that at the end of the day will set the sort of limits.
Cool. Well, we're coming up pretty much to our hard limit here on these podcasts. So the last thing I want to give everyone a chance to do is there anything you want to plug going on in Denmark? You know, anything interesting you want to try to attract people to, or just promote?
Promote, well, so I tried during the last half an hour to say science@home.org. I mean, I think there are lots of interesting games that you can play, but I think I would like everyone to sort of in general to consider playing less normal games and more sort of citizen science games in general. So I think that will help. That will help all of us, and I think that will also help. I think that will also become a little bit more involved in the scientific progress, and I think that's the most important thing, that what the citizen science is doing now. It's really democratizing the knowledge about what research really is all about.
Wonderful. So yeah, I've obviously in part of this live broadcast and certainly our downloads on SoundCloud and iTunes, I put a link to Science at Home. Certainly go ahead and play. Every time you play, you generate more data for these guys, and these guys clearly have a plan for this kind of data and to really try and help out development of actual quantum technology. So I definitely encourage you, if you have a smartphone or laptop or whenever you get a free moment, play a game that actually generates data. So thank you again, Jacob, for joining us tonight. And yes, just go play all these games.
Thanks a lot for having me.
Thanks again. Cheers.